Alrighty, so let's take a look here at our first free response question. Okay. So, number 23, right? We're told that a car sells for $25,000 and is known to depreciate at a rate of about 10% per year, okay? Now, it's been a while since we've talked about problems like this, okay? We touched on stuff like this back on May 2nd, so it's been almost 2 weeks since we've seen, or since we first saw problems like this. I feel like we've seen a few here and there in the meantime. But it's been a few weeks since we've seen one, almost 2 weeks since we've seen one, since we first saw our first one, kind of thing. However, that being said, this is also a review from Algebra 1 as well, from 1b, okay? So, we want to write a function that represents the value of the car after X number of years since it's purchased. We're going to write the equation to model the situation. Okay, so the format that we're going to use to write exponential growth, okay, or decay kind of thing, and in this case, it's going to be an exponential growth or decay based on our problem here. What do you expect to happen? Decay, why? Depreciating, right? Going down in value, right? Okay, so that doesn't matter whether it's growth or decay, though. The format of the equation will still be the same. We'll have a times b to the x, okay, where a, okay, is the starting amount, or starting value, if you like, okay, and b is the growth or decay rate, or factor, I should say, not rate, sorry, factor. Okay. So, in our situation here, what is A going to be? What value is A going to be? 25,000, right? Okay, that's what the car sells for 25,000. That's its initial value, right? Its value is determined by the price someone was willing to pay for it, right? And then for B, all right, well, we're not going to put just 0.1 in, okay? So 10%, right, that is 0.1 as a decimal, or 0.10 if you like, as a decimal there. But we're not going to put that in for B because that would mean that we're going to take 10%, right? When you multiply by 0.1 here, if I put 0.1 in here, I'd be multiplying by 25,000 by 0.1. So I'd be finding 10% of it, kind of every year, every time I multiply by that 0.10. And, well, 10% is not quite right. It's going down by 10%, which means what percent of it are we really holding on to? Oh, question?
Yeah, that's the starting amount.
Starting amount. Mm-hmm. Yep. Mm-hmm. No, that's okay. Thank you for asking. If it loses 10% per year, right, then what percent of the value is still there, I guess we'll say? 0.9, right? 90%, right? Another way to think about this is your B value will always be equal to 1 minus R for a decay. Okay? And R, that is your percent there. Okay? Since it's a decay, we do 1 minus my percent as a decimal. If it was a growth, we wouldn't do 1 minus R. What would we do instead? 1 plus R, exactly right. We would add the percent change. But since it's 10% depreciation, we want to subtract the 10% from 1, the 0.1 from 1. And so that makes that 0.90, or the 90%. Okay? So every year, right, it's worth 90% of the year before. And that shows that. And we'll put a little X here for the number of years since it's purchased. Oh, I guess technically I should put f of X here, because it does say given f of X. So. Okay, just like that. Okay? And then it asks us, so any questions up to that point? Is there any questions up to that point? Yeah. We do, yeah. B will always be equal to 1 minus R for a decay. If it's a growth, it'll be 1 plus R, because you're going to add the R value. Okay? So this is for decay. Okay? And then B is equal to 1 plus R for growth. Okay? Now, we'll graph this thing. And the tool that will best help us out graphing this, right, will be our graphing calculators. So we'll type in 25,000, right, parentheses, 0.90 to the x. Okay, right, just like that. Graph it. Okay, and we see nothing. Why do you think we see nothing? Our window, right. Our window. Now, if you want to get some guidance, we can go to our table. So second graph, let's go to our table and see what our table says here. Okay, our table has our starting y value at 0, right? The y-intercept is at 25,000. So what do you think we should maybe change our window to be? Our y max shouldn't be 10. What should I maybe make it?
30,000.
Let's try like 30,000, right? Because 25,000 is like the y-intercept. So let's see if I can see it now. Ah, much better. Okay, much better there. So when I go to sketch down here, okay, am I going to want to count by ones on my y-axis? What should I probably count by? 10,000s, if you like, or 5,000 would probably work. But since you said 10,000, let's count by 10,000. So here's 10,000. There's 20,000. There's 30,000. Okay? It's going to be kind of squished down there, but that's okay. We can use it this way. I would say counting by 5,000 is probably okay too here. Would have been okay. Bless you. Okay? And then how about here? What do you want to count by here on the x-axis? Count by ones? Yeah, I think that's probably okay. We probably are fine with that, okay? So let's just go ahead and do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now it says be sure to label the axes. So we want to label the axes here. What do the x value numbers represent? The number of what? Number of years. And what does the y value represent? The what? Price or value, yeah. I'm going to say value of the car. All right. And so then how can we get some points for this graph? Go to the table in your graphing calculator, right? Just go to the table. Or you can just plug some points in if you want to, too. But the table already does it for us. So let's see, I've got the point 0, 25,000. That's an easy one. So here's 0, 25,000 would be right here, halfway through. I'll just pick some other points there. 1 is at 22,500. So 1, 22,500 it'll be something like, well, like right here, we'll say. Okay. 2 is at 20,250. Something like that. 3 is at 18,225. Something like that, maybe. 4 is at 16,403. Okay. And then, well, I guess I've got 5 points, so I can just go ahead and kind of connect the dots there. Okay. It looks kind of linear here, but it shouldn't be. But anyway, we just kind of, we'll do something like that. Okay. All right. Letter C, is this an example of exponential growth or exponential decay? Decay, right? And why do we say it was decay? Decay because, again, it's justify your answer. It's going down, right? Yeah, the car is losing value. That's a better way to put it. Yes, the car is losing value. But if you say the graph is decreasing, then that's okay too, right? I'll go ahead and put 10% per year. Okay. Saying that it decreases 10% or it's losing 10% per year both shows that it's an exponential decay. Well, it shows it's decay and it shows it's exponential decay, right? And decreasing by 10% every year shows that it's both decay and exponential decay as well. All right, anyway. Find the value of f of x when x is 5. Well, again, you can go to your graphing calculator here, okay? We can just plug 5 in for x. So f of 5 equals, you can also just type it in your calculator too, so it will plug into the function. I mean, 25,000 times 0.90 to the 5. Or you can just go to your graphing calculator here at year 5. There's the value. So it's going to be 14,762. Okay, actually it's 1662 and 25 cents. Okay, if you want to check what the exact value is, if you arrow over and highlight that answer, you can see it gives you the decimal there too. It just can't fit all the decimal on there. Okay, question? Would it be wrong? Would you get it wrong? I would really like you to try and do it if you can. I would like you to, but will I take points off? I don't know. It depends. You know, it depends. At 0.25, yep. Okay. All right, last one, letter E. After approximately how many years will the car be worth half of its original value? So let's see here. Well, what is half of its original value? Well, let's see. We got to do 25,000 divided by 2. So 12,500. So there's kind of a couple ways you could go about doing this. Okay? One way we could do it is we could take that 12,500 and set it equal to our function there, 25,000 times 0.90 to the x, right? And then solve for x. Or we could also graph the left-hand side, graph the right-hand side, find the point of intersection, right? You want to graph it here maybe? Does that sound good? Let's graph it here. You can also go to your table here and just see when do we get close to $12,500. Well, if you just look at the values here, right, it happens between year 6 and year 7. So probably in year 6, right, in year 6 it's going to happen because it's from between year 6 and 7 that we go from 13,000 to 11,000. So we're going to cross that 12,500, right? But again, let's actually solve it for exactness sake here. So I'm going to graph 12,500. There's my point of intersection. So second trace, intersect. And then there it is, 6.58 we'll say years. Okay. Nearest hundredth include units. So nearest hundredth, that's 2 decimal places. Include units, it's number of years, right? So 6.58 years. All right. Questions on any of that? No questions? All right. If there are no questions, go ahead and turn the page then. Yep. Mm-hmm. Okay, no questions. Go ahead and turn the page. We'll look at number 24 then. Anyone still looking at this number 23? Yeah. Yes? All right. Just let me know there, Mike, and we'll move on. Good. All right. Turn the page then. All right. 24. Carbon dating is a process of determining the age of certain archaeological artifacts of a biological origin, such as bone, wood, and plant fibers. A carbon-14 atom has a half-life of 5,700 years. Okay? So half-life, by the way, what that means is that, certain elements, or certain isotopes, I should really say, so certain radioactive materials, okay, since they're radioactive, they emit energy, but when they give off the energy, they change what they are, okay? And so the half-life is how long a certain quantity of this particular material, how long it takes for it to reduce to half of what it originally started with, okay? So no matter how much of this carbon-14 atom you have, if you have, 100 pounds of it or something like that, after 5,700 years, you will only have 50 pounds of it. Okay? Stuff like that. All right, maybe I should say grams and... Yeah, anyway, that's the same thing. Okay. The exponential decay function, this, determines the remaining percent as a decimal of carbon-14 after t years. Okay? So P of t is the remaining percent of carbon-14 after t years. Now notice here, I want to make sure we're all okay with this. Okay? This is 0.5, and this t over 5,700, that is in the exponent of 0.5. Okay, just to make sure you understand that. That is 0.5 to the power of t over 5,700. Okay, so this whole thing right here is in the exponent. T over 5,700 is the exponent. Okay, so the first question is, what percent of carbon-14 will remain after 11,400 years? Well, what should we do with this 11,400? yeah, what should we do with that 11,400 using our function here? What can we do with this to figure out what percent will remain? Yes, plug it in for t. Exactly right. This is a t value. Okay, it's number of years. So good job. Yes, p of 11,400. And again, p is going to give us a percent, so we're going to plug it in there. So it would be 0.5 raised to the 11,400 over 5,700. Okay, and now how should we go about finding the answer here? What should we use? The calculators, that's right. Okay. Actually, I think this one might simplify nicely. I feel like 11,400 divided by 5,700 is going to be 2. So, but anyway, we'll just type into our calculators here. Okay. Please be careful how you type this into your calculator. Those of you who have the older calculators, okay, you must put parentheses around your exponent. So for those of you that have older calculators, I'll show you here real quick. All right, it's got to look like this. 0.5 around, parentheses around the base, to the, and then parentheses around the exponent there. Okay, so just like that. 0.25, which is what percent? 0.25 is 25%. So 25% of the original, 25% of the carbon-14 will remain. Okay, from what we started with, after 11,400 years, only 25% will remain of that carbon-14 because the rest will have, decayed. Okay, for those using the old calculators, if you don't put parentheses around your exponent, this is what's going to happen. Oops. If you don't put parentheses around your exponent, this is what's going to happen. You get the wrong answer. Okay? So please, please, please put parentheses on your exponent if you use the older calculators. Okay? The newer calculators with the math print, you don't have to worry nearly as much about it. Okay? It'll all stay up in the exponent there. And so you'll still get the right answer there. Okay? The next question asks, after how many years? So we're going to solve for what variable here? After how many years? We're trying to find a number of what? T. We're trying to find t. T equals what is what this is saying, right? Will there be a 10%? Will there be 10% of the original carbon-14 atoms left? Round your answer to the nearest whole year. Okay? So that 10%, that's going to be our y value, except we're not going to put in 10. What are we going to put in instead of 10? What's 10% as a decimal? 0.1. So we're going to say 0.1 equals 0.5 to the t over 5,700. Okay, just like that. So that's 10% goes right there. And we're going to solve for t. Okay? Well, actually, we're going to either solve for t or we're going to do what to solve this? So either use algebra to solve for t here, or what else can we use to solve this equation? Graphing calculators, right? We can graph the left-hand side, graph the right-hand side, and find the point of intersection. Okay, so there's what I typed in my graphing calculator. 0.1 for the left-hand side, and then 0.5 to the x over 5,700, right? Because, again, that's what we've got here. X for t over 5,700. We'll graph it. And I don't see it at all. Let me try zoom 6. Go back to the normal viewing window. I think, let's see, 10%. All right, so these things don't look like they ever intersect, so I'm going to try going further to the right here. I mean, we are talking in like thousands of years, right? So let me try like going out the x max. Let me try going to like 20,000. See how that looks. Okay, there it did go down a little bit. All right, gosh, I don't know if I did it. Let's see here. Intersect. Okay, it does show here that after about 18,000 years, we do get that 10% there. So we'll say about 18,934.95 years.
You're supposed to round to the whole year.
Nearest whole year? Okay, 18,935 years then. Okay, so I had to extend my x-axis out way far there because, I mean, if I go back to my normal viewing window there, okay, there's my curve, but it looks like a flat line. And that's because we got to really extend things out here, okay, because you can see we're dealing with like thousands of years, right, for our x values there. So I got to go out really far. So like I said, 20,000 is what I extended there to be for my x values. And now I can see it going down, and it's going to hit 0.1 somewhere around in here. Okay, so like I said, 18,935 years, we'll say. Okay, now, if you don't feel super confident about being able to get that on your graphing calculator, like graphing it, we can also use logarithms here to solve this, right? Okay, we want to get this t out of the exponent. So what base of a logarithm do we want to use here? Log base what? Well, what's the base of our exponential? What's the base of our exponential here? What number is the base of the exponential? 0.5. So just use a log base 0.5 of both sides. Oops. Sorry, I'm kind of getting crowded in here. Zoom in some. There we go. Okay. So again, because we want to get the t out of the exponent there, we're going to use a log base 0.5 on both sides. Okay. Log base 0.5 of 0.1, I'm just going to leave that the way it is. And then this will simplify it. Well, those will cancel. We're left with just t over 5,700. Okay. And then what should I do to both sides of my equation here to get the t by itself? Multiply both sides by 5,700 there. Okay? I'm running out of space, so I'll put it over here. So t will equal exactly 5,700 times log base 0.5 of 0.1. Or again, if you type in your calculator, type in your calculator, 5,700 times log, oops, I'll go back to pretty print. Okay, so typing in my calculator, 18,935, just like we got before. So two different ways to do it there. You can actually solve it using the equation, using logarithms in the equation, or you can graph it. Okay. Questions so far on A or B? All right. Letter C, what is P of 0? What is P of 0? Well, 0 is replacing t, right? So what does a t value of 0 mean here? Yeah. So at the start, okay. What's p of 0 though? P stands for the what in this case? Percent, yeah. Okay. So maybe I should say not at the start here. We'll say something like the starting percent of carbon 14. Okay, starting percent of carbon 14 atom. Now, it says to find the range in the context of the situation. This one's not that bad if we just think about it, right? What's the range for a percentage? What's the highest percentage that we're going to talk about here? 100%. Okay, so that means 100 or, let's see here, I want to be careful. I guess it's going to be 1.00, right? Because we're doing our ranges, our decimals, our percents as decimals, I should say. So we'll start, 100% is our highest y value. What would make sense to be the lowest percent you talk about? 0. Right? And eventually we'll get there, so I would say to include the 0 too. So it's just between 0 and 1. But we're talking about a percent here. We don't even have to worry about looking at the graph or anything like that. Just think about the context. It's percent is the range, so it's got to be from 0 to 1 if you're talking about decimals. Okay, questions on 24? All right, let's look at 25 then. Turn the page. Anyone still writing on 24? All right, last one here then. Letter A. Let g of x be the inverse of f of x. Find the equation for g of x. So here's f of x. All right. How do we find inverses again? Well, let's change f of x to be y. And then what do we do with our x's and y's to find an inverse? Swap them. So we'll have x equals 3 to the y. And then we need to solve for y. Okay? Well, to solve for y here, what am I going to do to both sides? How do we cancel out 3 to the y? What cancels out an exponential? Not a root. A logarithm, right? Logarithms. What base logarithm are we going to use here? Log base what? Log base 3. So we'll do log base 3 of this side and log base 3 of this side. Okay? Log base 3 of x is going to stay log base 3 of x because we can't simplify that. But log base 3 of 3 to the y, that simplifies. The log base 3 and 3 will cancel. I'm running out of space, so I'll put it over here. So we'll have just y equals log base 3 of x. And so this is our inverse. Okay, that's our inverse right there. Now, folks, you might be able to see a shortcut here. What if it was f of x equals 5 to the x? What would our inverse be? If our function was originally 5 to the x, what would the inverse be? Log base 5 of x. Exactly right. If it was like 7 to the x, our inverse would be log base 7 of x. Okay? So when you have just a plain old exponential like this, okay, its inverse will be the logarithm with the same base. So 3 to the x, its inverse is log base 3 of x. If this was 7 to the x, it would be log base 7 of x. If it was 5 to the x, it would be log base 5 of x. So on and so forth. All right, now it wants us to graph both f and g here. And we can use our graphing calculators to help us with that if we want to. So remember, f is 3 to the x, and g is log base 3 of x. Okay, so you can go to your graphing calculators here and just get some points and connect the dots. I'll do 3 to the x first. Okay, I'll just go to my table here. All right, so let's see here. Well, 0, 1. Negative 1, 1/3, so something like this. And then negative 2.1, and then it just kind of is going to bottom out there. Let's see here, 1, 3. And then 3, 9. I don't think I'm going to fit this. Or 2, 9. Sorry, 2, 9. And I don't think I'll fit 1, 2, 3, 4, 5, 6, 7. I mean, you can kind of, if you want to, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll go ahead and do it something like up here. Okay, just kind of. Okay, so this is f of x. All right, and there's that horizontal asymptote at 0. And then we'll go ahead and graph log base 3 of x. Oops. Okay, again, there's my log base 3. Okay, go to my table. And again, just pick some values. You can see that, okay, at 1 we get 0. So 1, 0. Okay, 2, actually the next nice one is 3, 1. 3, 1 is the next nice one there. So 1, 2, 3, 1. Okay, and then the next nice one's going to be 9, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 2. Okay, like that. But don't forget, logarithms, that's not all for the logarithm. It also goes down too. We have a vertical asymptote here. Okay, so it actually goes this way at 1. So it's going to look like that. There are 2 functions, and this is g of x. Okay, so just be careful there. If you just rely on your graphing calculator's table, you're going to think that this is the only part of your logarithm function right there. Well, the logarithm actually goes down here, okay? And since it's just log base 3, the vertical asymptote is at 0. Okay? So 3 to the x has a horizontal asymptote at 0. Log base 3 has a vertical asymptote at 0. Okay, and hey, look, letter C. Okay. What is the vertical asymptote here of g of x? Where's that vertical asymptote? 0. X equals 0. Sure. Okay. What's the intercept of g of x? Or in other words, where does it cross the x-axis? Yeah, we have an x-intercept at, well, at what coordinates? 1, 0, 1, 0. Okay? And is g of x going to have a y-intercept? Well, it's got an asymptote at 0, so is it going to cross the y-axis if it has a vertical asymptote? No. So there won't be any, so there'll be no y-intercepts. Okay. What's the domain for this function? Again, we're just talking about g here. They're only interested in g, right? So what's the domain for g of x? What's the farthest left this function is going to go? Again, just g of x here. What's the farthest left will go? 0. 0 to what? Infinity. Okay, so that's the domain. What's the range of this function? Well, what's the lowest y value we're going to get to? Negative infinity to, what's the highest y value? It's going to keep going up, so it goes to infinity. Yep. All right. And then last but not least, find the average rate of change. And average rate of change really just means find the slope. Okay? We have 2 x coordinates there, so 1 comma, well, if you guys remember here, at 1, we had the y value of 0. Okay? And then at 3, okay, we're going to have the y value of 1. So it's the points, 1, 0, and 3, 1. Okay? And so, you know, we'll just do y2 minus y1 over x2 minus x1. So we'll have 1 minus 0 over 3 minus 1. And so 1 over 2. And there's our average rate of change. Slope formula. When you do average rate of change, that just means the slope. And so you've got your x coordinates right there, Mike. Find the matching y coordinates using either your graph or your table in your calculator there. And then just do the slope formula between those 2 points.